Now, looking at the question which we were given, the question actually says we were given a what? They said a T-beam is fabricated with a cross-section shown in the fig below. Now, this is the figure that we were given, which is a T-beam. And what are they asking us to do? They said what? They said we should calculate the maximum bending stress induced in the beam by what? 5 kilonewton bending moment. So what we are given here was we were given a bending moment. So we are given a bending moment. We are given a bending moment of what? 5 kilonewton meter. Now what we are asked to calculate for was what? Maximum bending stress. So we are asked to get what is your maximum bending stress. Now, the first thing you do is you look at what you were given because you use your known parameters to get your what unknown parameters, right? Now, if you look at the beam, this beam is characterized into two or is classified into two. The first thing we are seeing here is the up part of the beam, the top part of the beam, and we can call this what? Flank. And the down part of the beam joining the flank, which is what represented as what? Web. Am I communicating? So basically your beam is characterized into two. So what you are going to do is you are going to bring out the parameters for your flank and you bring out what? The parameters for your what? For your web. Am I communicating? Now let's do that. Now, the first thing you do is you're giving data. What's your data? You're giving data. Now go back to what we have here. Now for the flanks, let's consider which is this part of the T-beam. Let's consider this part of the T-beam. Now, considering this part of the T-beam, we can see that we have 140 millimeter here and we have what? 40 millimeter, right? So here for the flanks, flank or flange, anyhow you put it, anyhow you call it. So here we have this plane figure, which is actually a rectangle. So they said from this point down to this point is actually what? It's actually 140. So we have 140 millimeter here, while from this point down to this point is what? 40 millimeter. So this is serving as our height, and this is serving as our what? Our width or our breadth. Am I communicating? So the first thing we do is we can put down the data, the width of the flanks, which is BF. So BF is equal to the width of the flanks. What are we saying? 140 millimeter. So we have 140 millimeter here. Now, next thing we are seeing is the height of the flanks, the height of the flank. Now, we can represent the height of the flank to be H subscript F. And we can see that H subscript F is what? 40 millimeter. Now, if you have a plane shape like this or a kind of a plane figure like this, what should come to your mind is what? Area. You get the area for the flank. Am I communicating? Now, considering area here, we know that area is what? Length times what? Times breadth. But in this case, we can see that our area here is simply what? Breadth times what? Height. Am I communicating? Which is still the same thing. Now, if we are considering the area here, we'll simply have what? 140 millimeter times what? 40 millimeter. Am I communicating? Now, if you punch that with your calculator, you will simply arrive at what? 5,600 millimeter square. Remember, area is millimeter square, millimeter multiplied by what? Millimeter, which you arrive at what? Millimeter square. So we can say that AF here, which is the area of the flank, is equal to the area of the flank is equal to 5600 millimeter square. Am I communicating? Now, the next thing that should come to your mind is to consider the centroid. of this plane shape. Remember, we were given a T-beam. This was our T-beam given. Now they said a T-beam is fabricated with a cross section shown in the fig below. Am I communicating? Now our interest is to calculate for the maximum what? Bending stress. You cannot calculate the maximum bending stress of this plane shape without getting the point of equilibrium of this shape. When I mean getting the point of equilibrium of this shape is where are you going to place your pen to achieve a stable nature here? Am I communicating? That is why we are to look for the centroid of this plane shape. Getting the centroid of this plane shape is you cannot just get the centroid, the full centroid of the T-beam, but rather what you do is you get the centroid for the flank and you get the centroid for the what? For the web. Am I communicating? Now to get the centroid for the flanks, remember when we are considering centroid, centroid is what? Centroid is basically half of your what? Half of your height. So now your centroid here for this plane shape will simply be what? HF divided by what? 2. And what's your HF? HF is simply what? HF is simply 40, right? So you have 40 divided by 2, which is equivalent to what? 20 millimeter. So if you've gotten your centroid, let's call this y of f. And we said y of f is now what? 20 millimeter. Am I communicating? So basically, you've succeeded in getting the centroid of your plane shape. So since we've considered the flanks, let's consider the web as well. Now, for the web, we simply have this figure. For the web, we are simply considering what we have here from this point down to this point. This is our web. Now, if we are considering this point, we'll simply have that for our web, we have a figure like this. We simply have a figure like this. Now, from this point, here is what? 25 millimeter, which is serving as the width. Then the height from the top to the bottom is what? 150 millimeter. Am I communicating? Now, the first thing you do is for the web, you will simply have your BW, which is the breadth or the width, to be 25 what? Millimeter, right? Then you now consider the what? The height of the web to be what? 150 millimeter. Am I communicating? Now, the next thing that should come to your mind is since we have a kind of a plane shape of this nature, it's still a rectangle. So we are considering the area of this shape. If you consider the area of your web, the area will simply be what? 25 millimeter times what? 150 millimeter. For those that are still confused on how to get the area, this is a rectangle. What's the area of a rectangle? Length times what? Breadth. But in this case, we have the width and we have the what? Height. So it's still the same thing as having what? Width times what? Height. Am I communicating? Now, if you do that, you will simply arrive at punching 25 times 150 millimeter in your calculator. You will simply arrive at what? That will give you what? That will simply give you 3750 millimeter. So you have 3750 millimeter square. Square is because it's an area. Am I communicating? You've succeeded in getting the area of the web. Area of the web is what? AW. And what's AW? AW is simply what? AW is simply 3750 millimeter square. Am I communicating? You've succeeded in getting the area of the web. Now, the next thing is to consider the centroid. Consider the centroid of your plane shape. Remember, I told you that when you are considering the centroid, you are considering what? The height of the shape. Now, what's the height here? The centroid of what we have here will simply be what? HW divided by 2. But remember, from our given figure, we had another height which was what? 40 millimeter. So we are to consider the height of the web with respect to this height here. Am I communicating? So now the centroid for your web will now be HW divided by 2 plus what? This additional height that was here, which is now what? 40. Am I communicating? Now, if you go back to our given data sheet, you simply have that your centroid here, which is what? YW will now be HW divided by 2 plus what? 40. Am I communicating? Now, what is HW? HW is simply what? 150 divided by 2 plus what? 40. And that will give you what? 115 millimeter. Please confirm that with your calculator. Now, what's the next thing? You've calculated the centroid for the flank and you've calculated the centroid for the what? For the web. Now we've also calculated for the area for the flanks and we also calculated for the what? Area for the web. Now the next thing is to calculate for your total area. What is now your total area? Your total area is the addition for the area of the flanks and the area of the what? Web. This is what we have here. So we have your AT to be equal to what? AF plus what? AW, which are the areas which we calculated for. Now, if you do that, if you sum both of them, you are simply getting the area for the T-beam, which is now what? 9,350 millimeter square. Now, remember, our interest is to get the neutral axis of your T-beam. How do you now achieve the neutral axis of your T-beam? You can only achieve the neutral axis of your T-beam when you've calculated for the distance from the top to what? To the point where you get your neutral axis. But since we don't know the neutral axis, we can calculate the distance from this point to the point where we can achieve a stable nature, which is a kind of the point of an equilibrium. Am I communicating? Now, the only way you can do that is to calculate for the area of the flank with respect to the what? To the centroid plus area of the web with respect to what? To the centroid. So if you want to do that, if you want to calculate for the distance from this point to the point where we have a neutral axis, we can say that YNA will be what? I told you, if you are doing that, you are going to consider the area of the flanks, which is AF, multiplied by the centroid of the flanks, which is YF, right? Now, plus you're now considering the area of the web, AW, with respect to the centroid of the web, which is YW, divided by the what? The total area of the what? Of the beam. Am I communicating? Now, if you do that, you simply have that your YNA will now be equal to AWYW plus what? AF YF divided by 80. Am I communicating? Now, what is now your AW? Your AW, remember, your AW, your AW was 3750. So you have 3750 millimeter square multiplied by what? One multiplied by 115. This is 115 millimeter plus what is now for our flanks. If we are considering our flanks, we are considering 5600. So we have 5600 millimeter square multiplied by 20. So we have multiplied by 20 millimeter divided by what is now the total area. What was our total area which you calculated for? Your total area was 9350, right? So if you do that, you simply have here to be, what you have here is what? 9350. Now, if you punch your numerator and you divide that with your denominator, you simply have 58.099 millimeter. Now, you've succeeded in getting the distance from this point to your neutral axis, but you don't know the point of your neutral axis. Am I communicating? So we can take the distance from this point. Let's say this is 40, right? From this point to this point is 40. So we have to count 58.0. So we are just estimating 58 to be around this point here. So around this point, we now have 58 point what? 099 millimeter. This is not the point of your neutral axis, but this is serving as the distance from the top of the beam or the distance from the flanks to what? To the neutral axis. Am I communicating? Now, remember, our question was to get the maximum bending stress and not the neutral axis. How do you do that? What formula do you apply when we are considering bending stress? Remember, when we are talking about bending stress is actually given with what? This, and we said this is equal to MC over what? I, where your M is now what? Your bending moment, your C is now the distance, while your I here is simply what? Moment of what? Inertia. Am I communicating? Remember, from our question, the only value which we were given, the only parameter which we were given was what? Bending moment. They said we have a bending moment of what? 5 kilonewton meter. Remember, we are not working with meter, we are working with what? Millimeter. So what should come to your mind is you were given M here, and we said M is what? 5 kilonewton meter. Remember, we have kilo here, so you convert this kilo, you take this kilo away. Taking that kilo away, you simply have 5 times 10 raised to the power of 3 Newton meter. We are not working with meter, we are working with what? Millimeter. So what you do is you convert your meter to what? Millimeter, by timesing this with what? 1000. Now if you times that with 1000, you simply have that the value you have here will now be 5 times 10 raised to the power of what? 6 Newton millimeter. So we succeeded in getting the real value for bending moment, which is what? 5 times 10 raised to the power of 6 Newton millimeter. Am I communicating? What are we seeing here? Moment of what? Inertia. Moment of inertia. Now, what should come to your mind is, how then can we calculate for the moment of inertia for our T-beam? How then can we calculate for the moment of inertia for our T-beam? Moment of area of the neutral axis. So if we are to do that, let's go right to a new page. If we are to do that, remember I told you that this is what? Maximum bending stress is equal to, your maximum bending stress is equal to what? MC divided by what? Moment of inertia. Now will now be equal to, your I now will now be equal to IC plus what? AD square. So meaning you are to calculate for, before you calculate for your moment of inertia, you need to calculate for the moment of area of your what? Of your neutral axis, which is what? This formula which we have here. Now from what we have here, from the formula we have here, we can see that our IC simply stands for what? Moment of inertia about your centroidal axis. So your IC, take down, your IC simply stands for the moment of inertia about our centroidal axis of the shape. Moment of inertia about the centroidal axis of the shape. Your A here simply stands for area, right? While your D simply stands for the distance between the centroidal axis and the what? And the neutral axis. So now we are having a new kind of a new form of, will I put it, will I say English in this case? What are we now hearing? Centroidal axis. Centroidal axis. So we are to consider the centroidal axis of our plane shape with respect to our neutral axis here before we can get the moment of inertia. That is what we are trying to say. Now, before you can calculate for the moment of inertia, we need to calculate for three different things. Now, the three different things which we are going to consider is The three things we are considering for the moment of inertia is for the flanks. We are going to consider three things for the flanks, and we are also going to consider three things for the what? For the web, which if we add both of them together, we are now going to consider what? Six different properties. Remember, our interest is what? Neutral axis, not centroidal what? Axis. Our interest is now what? Neutral axis. Now, what are the three things which we are going to consider for? Now, the first one is what we call moment of inertia of the flanks about its centroidal axis. So the first thing which we are going to consider is what? Moment of inertia of the flanks about its centroidal axis, and it is given as what? ICF. Moment of inertia of the flanks about its centroidal axis is given by ICF, and ICF is equal to BF multiplied by what? HF raised to the power of 3 divided by what? 12. This formula is applicable for only when you want to calculate for the moment of inertia of the flanks about its centroidal axis. And what will you simply have? Let's impute the values. Now, if you input the values, what is our BF? Remember, our BF was the breadth of the flanks. Now, if you come back to our given data, you can see that the breadth of the flanks was given as what? 140 millimeter. Now, here we'll simply have our BF here to be 140, right, millimeter. Don't forget to input your values, multiplied by what's HF. HF was given to be 40, height of our flanks. So we have 40 millimeter, but in this case we have cube up. So this is raised to the power of what? 3 divided by what? 12. Am I communicating? So what you simply do is you punch this in your calculator and you simply have this value 7466 point what? 67 millimeter raised to the power of what? 4. Now this is the first thing. Now the second thing is to get the distance from the flanks centroid to the neutral axis. So the next thing here, the number 2, which you are going to look for, is now the distance from the flank centroid to the what? To the neutral axis. So and that is denoted with what? That is denoted by DF. And DF is equal to, since we are considering the distance, we are going to consider the distance for the what? For the flank centroidal axis with respect to the distance to the what? Neutral axis. So we are subtracting the distance from the top of the beam. So we are considering the distance from this top down to the neutral axis minus the centroid of the what? Of the flanks. Am I communicating? And that will give us what? So we simply have YNA minus YF, and this is simply what? What's your YNA? Your YNA is simply 58.099 minus what's now the centroid of your flanks. And we calculated the centroid of our flanks here. What's the centroid here? 20. So we calculated for the centroid of our flanks to be 20. So we have 20 here. And what will this give you? This will simply give you, if you punch this on your calculator, you simply have 38 point what? 099 millimeter. So this is actually what? 38.099 millimeter. Are we done? Done. Now the last thing which you are going to consider is the what? Moment of inertia of the flanks about its centroidal axis, which is what we are interested in. So the last thing which you are to get is what? We are to get what? The moment of inertia of the flanks about its centroidal axis, which is denoted by what? IF. This is our interest. So what is our interest? The interest is for you to get the moment of inertia of the flanks about its centroidal axis. What you do is you pick what you have here, then you add it with the area of the flanks with respect to the distance of the what? Of the flanks. So what we are going to do is we are going to pick the centroidal distance, axis distance, which is ICF plus AF multiplied by what we have here, which is what? D subscript F raised to the power of what? 2. So this formula is applicable when you want to calculate for the moment of inertial of the flanks about its neutral axis. And this is equal to, what's our value we got here? The value we got here was what we have here, which is what? 74666 point what? 67, right? Plus, what's now the area of the flanks? The area of the flanks, we have the area of the flanks to be 5,600. So we have here 5600, right? Multiplied by the distance here. So multiplied by 38 point what? 099 square. Am I communicating? Sorry. Now, if you punch that with your calculator, you'll simply arrive at the value to be, you simply arrive at this value, which is what? 8875234 point what? 67 millimeter raised to the power of what? 4. So we succeeded in calculating for the distance, for we succeeded in calculating for the moment of inertia of the flanks about its centroidal axis. Now remember, everything we were doing here was what? For the flanks. For the flank. Is it flank we call it or flanks we call it? Anyhow we put it, just know that what we calculated for was for flags. Now let's consider the web. Let's consider for the web. Now, considering for the web, the first thing I told you, there are three things. Now, the first thing will actually be what? The moment of inertia of the web about its centroidal axis. So we have the first one, which is what? ICW, right? Now, what will be your ICW? Your ICW will simply be what? BW multiplied by HW raised to the power of 3 divided by what? 12. So what we have here is simply the formula for you calculating the moment of inertia of the wave about its centroidal what? Axis. Am I communicating? Now, if you input your values, you simply have what? What's our BW? Our BW is what? 25. So we have 25 millimeter multiplied by HW. HW was what? 115. So you can do well to go back to your data sheet. Sorry, go back to your data sheet. This is divided by what? 12, right? Now what you do is you punch what we have here in your calculator. Punching that in your calculator, you simply have what? 7031250 millimeter. Now what's the next thing? The next thing is to calculate for the distance from this web centroid to the neutral axis. The next thing is to calculate for the distance from the web centroid to the neutral axis, and that's denoted by what? DW. Now for you to calculate for your DW will simply be what? YW, which is the centroid of the web, minus the distance from the top of the flanks to the neutral axis, which is what? YNA. And this will give you what was our centroid for our web. The centroid for our web was given to be 115. That was what we calculated for. Let's confirm. So the centroid of the web, which is this, was what? 115. So we are correct. Now, if you do that, we are simply putting 115 millimeter minus what's the centroid from the flanks to the neutral axis was now what? 58 point what? 099 millimeter. And if you punch that with your calculator, you simply arrive at, I think, 56 points. 0.901 millimeter. Am I communicating? Please confirm the value and drop it on the comment section as well. Now, what's the last thing you have to do? The last thing which you have to consider is the moment of inertia of the web about its what? Neutral axis. Now, the last thing which you have to consider for is the moment of inertia of the web about its what? About its neutral axis. Now, what do we do? The moment of inertia of the web will now be denoted as what? I subscript W. And I subscript W will now be what? What we've calculated for here, which is what? ICW, right? Plus the area of the web, AW, multiplied by this distance here, which is the distance from the centroidal axis to the what? To the neutral axis. The web centroidal axis to neutral axis will now be what? DW raised to the power of what? 2. Now, if you do that, you simply have this value, which is what? 7031250 plus what's the area of the web? We calculated for the area of the web to be 3750, right? So you go back to what we have here to be what? 3750, right? Multiplied by what's now the distance of the web. Remember, the distance of the web is now what? 56.901. So you have the distance of the web here to be what? 56.09, 56.901, right? Now, if you punch this with your calculator, please confirm this value. From what I have here, I simply have what? 1 1. I simply have 191.72700 millimeter raised to the power of 4. Confirm the value and drop it on the comment section.